In this video, I explain the I2C protocol used in serial communication for just a master and a slave, while the protocol supports multi-master and multi-slave communications using just 2 wires. This protocol supports different features and offers a simple and efficient way to interconnect devices while using minimal I/O pins. Let's dive into this protocol that I used to interconnect breadboard Artemis Nano with a 6 degree of freedom inertial motion unit in my next video. This is very common serial protocol for short distance data communications. In this protocol, both master and slaves can send or receive data. This is just a synchronous protocol. I2C can be run in different clock speeds. This figure simply describes the topology of an I2C with a master that we mainly use the breadboard Artemis Nano and a number of slaves, which here are different inertial motion units. As mentioned, there are different nodes that one of them is always master device that initiates and generally controls the communication with one or more slave devices. The master is connected to all slave nodes through 2 lines of communication, namely SCL, serial clock, and SDA, serial data lines. The master device generates the clock signal on the SCL line and uses the SDA line to transmit data to slave devices or receive data from them. Note that SDA and SCL are connected to voltage by single pull-up resistor. I do not, however, discuss about the pull-up resistors for the sake of simplifying this video. A general overview of I2C serial communication is given here before diving into a more detailed description. The first step is the claim of the bus by the master through the start condition. After specifying the slave and master nodes, the master sends the address of the slave node, followed by a bit that indicates whether the master aims to read data from the slave or send data to the slave. At this point, it is the slave's turn to confirm the receipt of this information. By sending its acknowledgement to the master. Once the slave has indicated that it's ready for data transmission, a byte of data is transmitted. In this video, my main focus is on reading data from the slave. The slave then confirms the receipt of this byte by sending an acknowledgement. The process continues. with transmission of subsequent bytes, each followed by an acknowledgement until the data bytes have been transferred. Finally, the communication is terminated by employing the stop condition. In the coming slides, I will explore each of these steps in more detail. When the bus is idle, both the SDA and SCL lines are pulled high by pull-up resistors connected to the power supply voltage. This ensures that the lines remain at a high logic level when no communication is taking place. The start condition is initiated by the master device, which claims the bus. To generate the start condition, the master device pulls the SDA line from idle high state, logic level 1, to low state, logic level 0, while keeping SCL line high, and SCL pulls low right after the SDA, as shown here. Hereafter, it is master that sets the stage for addressing and data transfer. Let's understand how master coordinates addressing. Each node have to have fixed address. Here I need to remind the most significant bit MSB and the least significant bit LSB. The bit with highest value is called MSB. For example, in 4-bit binary code 1001, the MSB is 1, 2, 4, 8. MSB is then 8, and the LSB is 1. The address of a slave node comes right after a start. The address is commonly a 7-bit address starting from the most significant bit A6. Here we need to understand the concept of timing between the SCL and SDA signals. That is crucial for reliable data transfer. The timing is determined by the clock frequency and the data rate selected by the master device. During data transmission, the SCL line generate clock signals as shown here. For example, in the clock signal shown in this figure, we have two rising edges and two falling edges. The SDA line does not change its state, high or low, between rising and falling edges. As shown in this figure, SDL changes between falling and rising, but not between rising and falling edges here. Let's move on and see what happens next. After address data, we have read-write bit that is used by the master device to indicate whether it intends to read data from a slave device or write data to it. Just in short, in addressing mode, master sends a 7-bit address of the slave device followed by the read-write bit as the 8th bit, becoming overall a byte. This byte is then followed by one acknowledgement ACK bit from the receiver. The ACK bit allows the receiver or a slave with correct address to communicate to the transmitter that the byte was successfully received and another byte may be sent. It is worth noting that to send an acknowledge bit, the receiver shall pull down the SDA line during the high phase. The SDA line is stable high. We now send data in a byte or 8 bits, starting by the most significant bit. If we have multiple bytes, after each byte, master should receive an acknowledgement from a slave before exchanging the next byte. This bit is 0 if data has received. Here the slave confirms its readiness for the next operation. I just recall that the I2C in idle condition is high, and if no response occurs from the slave, the SDA line becomes high, indicating a non-acknowledgement bit or NAC bit. The communication is then terminated by generating a stop condition on the bus or repeating a start condition. The stop condition is responsible for indicating the end of data byte transmission and communication. During the stop condition, the SCL line returns to high and remains high, followed by SDA line returning to high and remaining high. The bus then enters an idle state with no clock signal until the next start condition is generated. In this video, I explained the I2C as one of common serial communication protocol that uses only 2 wires for communication, namely SDL and SCL lines. We explored briefly the topology of an I2C communication protocol and its different components as shown in this figure. I will continue in next video on how to use I2C communication to collect accelerometer and gyroscope data from a 6 degree of freedom IMU inertial measurement unit sensor. It is noted that SDL and SCL idle state is high. I have not explained here about the pull-up resistors and different bus speeds, and this may be done in another video.